Millikan, Faraday, and Nernst are often praised as some of the founding fathers of electrochemistry. But just as with so many other forms of chemistry, the so-called founding fathers were really the lucky Westerners who brought modern scientific method to bear on it for the first time. In truth, the phenomenon of electrical current might have been observed and even used long before any of these men drew breath. There are those who believe that ancient Sumerian cultures may have developed crude devices to use as batteries for processes requiring mild electrical current. Now, these devices, sometimes called Baghdad batteries, were discovered in the 1930s. They caused quite a buzz in the archaeological community because they appear to have contained copper, iron, and an acidic solution, all the ingredients required to create an electrochemical battery. Now, the debate over exactly what these objects are and how they were used thousands of years ago raged for decades, but archaeologists couldn't seem to agree on their intended purpose. It's remarkable, isn't it? Also very sad because this story involves a tragedy, as these hard-to-believe relics of a pioneering civilization were destroyed in the chaos and unrest that plagued the area just a decade ago as Saddam Hussein's regime was unseated. Among the casualties of that conflict were the Baghdad batteries, then housed in a museum in the land in which they were created thousands of years ago. With their loss, we may never know for certain what they were used for or the extent of these ancient people's understanding of electrical power. So humanity and electrochemistry might have had a brief, tenuous encounter thousands of years ago. That encounter may very well explain some unanswered questions about how ancient cultures were able to make some of their remarkable accomplishments. Although there's evidence that ancient peoples as long ago as 2500 BC just might have had a modest command of electricity, the origin of the term battery can be found in a much more recent history, as humanity's command of electricity began to firmly take hold in the years leading up to the Industrial Revolution. Notable American statesman and researcher Benjamin Franklin is generally given credit with first using the term battery, which is now a household word, of course. Franklin did not have the advantage of a modern electrochemical cell, so he conducted many of his electrical experiments using a device commonly known as a Leyden jar. Leyden jars are glass jars with metal plating both inside and outside of the jar. These plates are separated by a gap at the mouth. These jars were not able to produce electrical current on their own, but they did have the intriguing ability to store electrical potential. Franklin is famous for rigging multiple Leyden jars in a series to help increase their storage capacity. He used the term electrical battery to refer to the fact that multiple cells of the same kind were combined, a battery of cells. Franklin may get the fame for first using the modern name for electrical storage devices, but our modern understanding of them finds its origins in late 18th century Italy. There are two fathers of modern electrochemistry here, Alessandro Volta and Luigi Galvani, and they were engaged in an argument. Galvani had placed the legs of recently dissected frogs on brass hooks for observation. Galvani noticed that when he touched the brass hook with a probe made of a different metal, the legs twitched. Galvani knew that electrical impulses were associated with muscle contraction, and his conclusion was that he had tapped a new form of electricity, one generated by the muscles in the frog's legs themselves. But Galvani's contemporary, Volta, had a different idea. Volta believed that the twitching of the muscles was not the source of electrical current, but rather a consequence of it. Volta's theory was that the frog legs did not generate current, but rather that they were responding to current created when the two different metals, in this case a brass hook and an iron probe, were brought into contact. So Galvani's theory centered on biologically produced current, and Volta's contrary theory stated that current could be generated without a biological material at all here. Now, if you were Volta, how would you go about proving Galvani wrong? Of course, construct an apparatus that could create current without the aid of the biological component. And that is exactly what he did. Volta piled alternating disks of silver and zinc, each separated by a disc of leather, cardboard, or some other insulating material. The separating material was soaked in a solution of salt before being placed into the pile. And when the top of the pile was connected to the bottom with a conductive wire, an electrical current could be observed flowing from one end to the other. Volta's construct looks quite crude in comparison to modern batteries, but it was the first real example of sustained, steady electrical current produced under controlled conditions. Not only that, it's so simple and reliable that you can make one yourself. Volta's creation is easily recreated in your kitchen at home using materials that you have handy, I'm sure. What we're going to need to build our own voltaic pile is some kind of a paper plate or construction paper, a little bit of ordinary table salt. I've got some distilled water here as well. And then we'll need zinc washers, which you can get at a local hardware store, and just a few nice clean pennies from your pocket. These will be substituted for the silver discs that Volta used. Now, if you can't find zinc washers, you can also use something like this, the knockouts from a junction box. These are also coated with zinc and will do just fine as well. Now, you'll also notice that I took one of my paper bowls here and I cut it into discs that are roughly the same size as my pennies and my zinc washers. Now, to begin building my voltaic pile, I need to create a very strong salt solution. So in order to do that, I'm going to take my distilled water and basically a spoonful of salt and mix those together. And the concentration's not critical here. What's important is that we have enough salt in there that it can conduct electricity well. So I'm going to let that dissolve after stirring a bit. And then I'm going to start work on my pile while that salt soaks for a little while. I like to use a metal bracket as a base. It's not really essential to the pile working, but I'm going to put that out there anyhow. And I'll put my safety glasses on again, just because I'm working with a solution. Now, remember, Volta stacked his pile in a very specific way in order to generate a voltage. I'll begin building my voltaic pile by placing one of my zinc washers directly on this metal plate here that I have, just to give me a nice flat surface to build on. The next element of his pile was something soaked in a salt solution, like a piece of leather or cardboard. I'll have to grab one of my cut paper plate wheels here, my tweezers. And then I'm going to submerge that in my salt solution so that it can soak some in. Being sure that when I remove it, I shake any solution loose, because I only want what's been soaked into the paper plate. So if I have extra salt solution there, I'll just shake that loose so that it won't cause a short circuit. And I'll place that on top of my zinc washer. The third and final element, of course, for Volta's creation was a disc of silver. We're going to use a penny because the copper plating on the penny can do the same job. Now I've created a single cell of a voltaic pile with a zinc washer, a salt solution soaked disc, and a copper penny. Now I can measure the voltage across the cell by placing my probes on either side, one on the copper, one on the zinc. And I measure a voltage of about 0.76 volts. This is exactly what's expected for a voltaic pile that has one cell. But I may need more voltage than that to accomplish whatever goal it is I've set for myself. And what Volta did was to pile up multiple cells, one upon the other, to create higher and higher voltages, which I can do myself by placing another zinc washer, another one of my discs soaked in salt solution. Just let that soak up for a moment. And then be sure that I remove any excess so that I don't end up short-circuiting my voltaic pile. Place that on top. And finally, another penny. So that completes the second cell in my voltaic pile. And if I go back to measure the voltage, notice that my voltage has increased to 1.5 volts. It's double because of the second cell being present. So in this way, Volta discovered that he could build a pile that delivered any voltage necessary simply by adding more and more cells to the stack. So we've established that a voltaic pile can create an electrochemical voltage simply by stacking one cell on top of the other. And of course, this opened up a whole new avenue to create work. In this case, I'm just going to light a light bulb here using my voltaic pile that I've created, attached an LED through some alligator clips to these two wires, and by touching them to alternate ends of my voltaic pile, I can light the lamp. Volta's creation didn't only help him win his debate with Galvani. It was very quickly realized by many preeminent scientists of the day just how useful this product could be in research as fundamental as discovering elements themselves. Most of the credit for this is often given to Humphrey Davy, who famously discovered a half-dozen metallic elements with the voltaic pile. Davy realized that he could decompose certain inorganic substances simply by placing wires into a liquid sample of whatever compound he suspected was composed of multiple elements. This made the decomposition of water into its elements simple in comparison to methods employed by Lavoisier just a few decades earlier as well. Davy also found that as current ran through molten samples of potash and soda ash, a pure metal would begin to form on the cathode. He named his new elemental discoveries potassium and sodium in reference to their sources. Davy went on to use this technique to discover most of the alkaline earth metals, including magnesium, calcium, barium, and strontium. He famously performed demonstrations of his reactions throughout London on many occasions, achieving a sort of a celebrity-like status, like that of a street magician. Indeed, his demonstrations must have seemed magical, dipping the wires of a voltaic pile into a liquid substance, only to produce a shiny but reactive metal at one end and an effervescing oxygen gas at the other. It must have been quite a spectacle to see in that time. Of course, all of this was leading up to Mendeleev's conception of the modern periodic table with his game of cards. So if Mendeleev was the card player, one could say that Davy was the dealer, and it was the cards themselves that were made possible by the voltaic pile. Of course, today's batteries look a bit different than voltaic piles did some 200 years ago. They all operate on the same principle. Reduction and oxidation half reactions are separated in space and can only run when they're connected by an electrical circuit. But we have so many different electrical needs in the modern world. Our cars need a quick, powerful jolt of electricity to start up their gasoline engines. Many simple tools like flashlights require a long, steady current delivery. And portable electronics like our computers, phones, and music players need power sources that are not only light and small, but can be recharged over and over again. So chemists and engineers have their work cut out for them. With so many different needs to be met, can we deliver products that accomplish all of these needed goals? So far we have. And it's led to the creation of a number of electrical battery technologies that many of us take for granted today, but that required decades or even centuries of careful research and testing to perfect. Let's take a look at a few of them now. Automobiles have a long and influential history. One has to search very, very carefully to find even the smallest community that does not rely on motorized vehicles anywhere in the world today. Now, the earliest prototypes of what can truly be thought of as automobiles were crafted in the late 1700s, 1768 to be exact. Not surprisingly, this innovation first came into being in France, a scientific powerhouse at that time, being home to minds like Lavoisier in the latter half of that century. But the innovation that we're talking about here was devised by another Frenchman by the name of Nicolas Joseph Cugnot. Cugnot created a steam-powered vehicle for the purpose of transporting cannons across the battlefield for the French army. His design may appear crude to us today, but we owe a great debt of gratitude to him for proving that locomotion of such a vehicle was possible without the use of a beast of burden. And it didn't take long for the world to have the revelation that if you could make a vehicle to pull something as large as a cannon, you could make one to move a person. For nearly a century after Cugnot's invention, many other ingenious souls lent their talents to the design of machines intended to make our lives easier by moving us and products that serve us from one point to the other. Not surprisingly, a contest of the minds ensued over exactly how to power these vehicles. Cugnot's steam design was refined by others as the decades and centuries passed. Automobiles with electric power and combustion engines eventually entered the race for dominance on the roads of America and Europe. Of course, ultimately, we all know which technology took hold in the late 1900s, the gasoline engine. But what we don't think about very often is that, ironically, one of the devices that did bring the gasoline-powered vehicle to the forefront was actually an electrical device. You see, gasoline engines need to be cranked to start. The piston must cycle a few times under the force of another device before the engine will cycle on its own. This was a real sticking point in the early 1900s, as gasoline-powered vehicles required an operator to get out, walk around to the front, wind a spring-loaded crank to provide the energy to start the engine. Not the most inviting proposition for a gentleman on his way out to impress the world with his new ride, or a worker on his way to the office on a cold morning. But what if that weren't necessary? What if a gadget could be used to do the work of cranking up the engine and at the push of a button or at the turn of a key? Now, this became possible when the electric starter motor was developed and paired with one of the most influential battery designs of all time, the lead-acid battery. The foundations of that shift were laid nearly a half-century earlier in 1859, when a Frenchman by the name of Gaston Planté built the first lead-acid battery. It looked a bit different than modern versions. Planté simply took 2 sheets of lead, placed a cloth in between them, and rolled them into a spiral. Now, this spiral was placed into a jar of dilute sulfuric acid, and each sheet of lead was connected to a wire. That's it. That's all it takes to make a lead-acid storage battery, at least the 1859 version. But it seems a bit unintuitive. Voltaic piles worked specifically because the 2 electrodes supported different half reactions. At first glance, Planté's design with identical lead electrodes seems like it would produce no voltage at all. In fact, that's exactly right. Planté's battery was not ingenious because it could create electricity like a voltaic pile, but rather because it could be charged using an external voltage and then discharged at will. So by placing a voltage across the electrodes, initially hydrogen was formed at the cathode and oxygen at the anode. The oxygen could then react with the lead sheet at the anode, forming lead oxide. Hydrogen, on the other hand, didn't react with lead at the cathode and simply escaped. Now we're in business. With the lead oxide plate for one electrode and pure lead for the other, we have all the makings of a battery, a cathode, anode, and a medium for the transmission of ions. So let's take a look at how a battery like this one works chemically. A so-called lead-acid battery generates current using 2 redox half reactions. Now, the first of these, again, is the reaction between lead oxide and the acid that's in the electrolyte of the battery. That's shown here. This has a cell half potential of 1.685 volts. Now, the other reaction that's taking place, of course, is the reduction half reaction. In this case, that's the lead itself reacting with the electrolyte on the other plate that has not been oxidized. And that actually has a potential of plus 0.356 volts. So the summation of these 2 reactions gives us the overall cell potential. So in this case, the overall reaction shown here generates an overall cell potential of 2.041 volts. This gives us a very easy way to construct batteries that deliver voltages in multiples of 2. We simply wire the appropriate number of compartments in serial to get the total voltage that we want. For example, the 12 volts in your car battery would require 6 of these cells be wired in this way. Modern versions of Planté's brainchild are often manufactured with a lead oxide layer pre-applied to one of the plates within a cell, eliminating the need for the electrolytic conditioning that Planté relied on to achieve the chemistry he wanted. In most other ways, the sealed batteries that you might buy at the auto parts store in your neighborhood are made of the same materials that Planté first mixed about a century and a half ago. The robust burst of current, rechargeability, and low cost of these devices makes them indispensable to us even now. Pop the hood of most modern automobiles and you'll still see a lead-acid battery staring back at you, waiting to provide a clean, simple start at the push of a button or the turn of a key. So Planté's lead-acid battery was perfectly suited for the burst of energy needed to start a car. But what about something that needs a bit more sustained energy? How about lamps, maybe your music player? These devices need more than just a quick electrical shot in the arm to operate. They take all of their operating power from electrical batteries. That means that a steady, sustained flow of current, which means a steady, sustained voltage is required. But the Nernst equation makes it clear that Plante's device can't do this very well. Remember, cell EMF is dependent on concentrations, and the acidic electrolyte is actually consumed when a lead-acid battery discharges. That spells trouble because the voltage delivered will change as the battery slowly dies. This is frustratingly all too real to anyone who has been stranded with car problems. That ever slower turnover of the starter or the slowly dimming headlights remind us that the voltage supplied by our battery is ebbing away. Now, short of those rare situations in which you are waiting for the auto club to come and help you out with a jump, lead acid does all right for your car. But if we want to use batteries as a portable substitute for that wall outlet, we need something more. Enter a completely different design in electrical batteries, the alkaline battery. In the 1950s, a Canadian researcher by the name of Louis Urey came up with the design for a modern alkaline battery. And although it can be made to look to the end user much like the lead-acid battery, its chemical design is actually very different. The so-called alkaline battery, or in this case one of its very early iterations, works on a chemistry something like this. The reaction that takes place in the oxidation half reaction is zinc reacting with hydroxide, hence the name alkaline battery, to produce a little bit of water, zinc oxide, 2 electrons, and 1.28 volts of EMF, electromotive force. In the reduction compartment of this battery is manganese oxide, reacting to form Mn2O3, another type of manganese oxide, but one in which it has been reduced. And there's actually another positive EMF here, plus 0.15 volts. So when we put these two reactions together, something interesting happens. Not only do we get a really nice delivery of voltage here, about 1.5 volts, but notice that in this particular reaction, there is no liquid, there is no gas, there is no solution, which means that Q from the Nernst equation is effectively 1. We basically eliminated the issue of non-standard conditions. And what this does is allows these batteries to run very smoothly and deliver nice, steady current, with the bonus that they aren't liquid. We don't have to worry about spilling their contents when they're turned over. So this so-called dry cell battery chemistry has gone on to become what we are all very familiar with as the alkaline batteries of today. Any one of us old enough to have owned one of these knows that when those alkaline batteries went out on your morning jog, the tape ground to a stop almost instantly. This is exactly because the alkaline design takes concentration out of the equation and uses a reaction custom-made to do just that, deliver long, steady voltage that dies almost in an instant. Now, in the early 1990s, a new technology was made mainstream when it was adopted by Sony Corporation and integrated into many of its electronic devices, especially the mobile ones. It was heralded as a breakthrough in battery technology, the lithium-ion battery. Light, powerful, and rechargeable. This battery technology is a part of many of the devices that we've come to find indispensable over the past 25 years. Our cell phones, portable computers, in some cases even automobiles and medical equipment, all can rely on so-called lithium-ion batteries. Credit for its design often goes to John Goodenough, who developed some of the very specialized materials needed to produce the brilliant devices while working at Oxford University. This little invention brought battery technology into the 21st century at a time when it was sorely needed. Computing power and portable computing devices were gaining popularity and in affordability at that time, and one of the most significantly lagging technologies holding these devices back was their power needs. Consider the framework for a lithium-ion battery cell. We start with graphite and cobalt oxide cells. Next, we add a layer of electrolyte medium between the two. Now, through this, ions can move. But we place a special membrane in the electrolyte between the cobalt oxide and graphite plates. This membrane is very special material designed to be permeable to lithium ions, but not to the other ions in the electrolyte medium. Now, connect the cathode to the anode with a wire, and nothing happens. Well, that was anticlimactic, wasn't it? Well, that's because we're missing something, and that something is those lithium ions for which the technology gets its name. Remember that the special membrane prevents ions in the electrolyte from moving back and forth between the cathode and the anode. Only those very special lithium ions have the ability to get through. So let's switch out some of the cobalt ions for lithium ions in the oxide layer to create the pioneering material developed by Goodenough. Now we're getting somewhere. Right now the lithium ions are happy located in the oxide layer in their lowest energy available state. The battery's not charged. But apply a voltage to the system, and the lithium ions can be pushed through the electrolyte, through the special layer that's permeable only to them, and finally over to the graphite anode layer beyond. And this balances the negative charge resulting from the applied potential. The battery is now charged, and it's ready to use. Remove the applied voltage used to charge the battery. Now those lithium ions are trapped in the graphite anode, but they want desperately to be back in the oxide layer that they came from when charging. 3.7 volts worth of electromotive force is poised to be unleashed when this happens. But if all those cations are going to flow back over to the oxide cathode layer, that charge is going to have to be balanced. Connecting the anode to the cathode by a wire or an electrical device gives those electrons a pathway to the cathode. This newer battery design has several immediate advantages over its predecessors. First, each cell produces 3.7 volts of potential, about 3 times the potential of a traditional alkaline battery cell. Second, the design is extremely robust and can be easily recharged hundreds or thousands of times without significant loss of storage capacity. And finally, as the lithium-ion battery has been advanced over the years, new electrolyte materials have made it one of the lightest battery options on the market. So you might say that the lithium-ion battery is positively ideal for use in portable technologies, like those that most of us have come to find indispensable. So let's sum up. Today, we applied some of our understanding of electrochemistry and electrochemical cells to one of the most influential inventions of all time, the electrical storage battery. We started by considering just how long ago the phenomenon of electrochemical storage might have been used, if not completely understood. And we considered how materials as simple as clay pots can be used to store and discharge electrical potential on demand, using these so-called Baghdad batteries as an example. We discussed the debate between Galvani and Volta in the 1700s over Galvani's curious observation of twitching frog legs. And we saw how Volta's part in the argument drove him to create the voltaic pile in his quest to disprove Galvani's biological energy theory. We were introduced to a device known as a Leyden jar, and saw how famous American scientist Benjamin Franklin discovered that connecting multiple Leyden jars together can create a so-called battery of electrical cells, increasing their power or discharge time. A curiosity in his time, Leyden jars are long forgotten, but his term battery has never faded. Next, we took a leap forward and considered some of the more familiar battery technologies to us, including lead-acid batteries developed by Gaston Plante, which steered the development of the automobile by delivering a burst of power for gasoline engines to start. Next, we explored the complex chemistry of the household alkaline battery, which gets its name from the hydroxide ions that participate in its electrochemical reaction. We saw how they're able to deliver steady, consistent power because of the solid state of the reagents that are consumed and produced in the reaction. But the need for heavy metal hydroxides makes them relatively heavy and unappealing to lug around. So finally, we explored the chemistry and design of the lithium-ion battery, a brilliant invention that delivers high voltages in a compact, lightweight, rechargeable package that relies on the motion of lithium ions to generate electrical current. The field of electrical battery development continues to rush to keep up with our power demands as a culture. Many new designs are being investigated every day, each lighter and more powerful than the last. But our time with electrochemistry is done, and we're about to move on to explore one way in which the power to charge all of these electrochemical creations is obtained. Next up, we're going to dive back into the structure of the atom itself and marvel at the power that's contained inside and how some ingenious researchers have found ways to release it.